Hello, everybody. So what we're looking at today is going to be section 5.2 in your book, which is double integrals over general regions. Um, so this is really just a continuation of what we started last time, where we were doing integrals over rectangles. So this time we get to mostly skip theory and kind of just solve a lot of problems. So what we're going to learn how to do is recognize a double integral over a general region. We're going to evaluate double integrals over general regions. We're going to learn how to switch the order of integration. And also we're going to solve area problems with double integrals. Okay, and that's what we're going to do. So let's go ahead and get started. First of all, what is a general region? That's the first thing we need to know. So when we say a general region, what we're talking about is something like this region D here in the plane. Okay, let's see here. Yeah, well, okay, fine. I don't really like the definition here, so like pretty much ignore the g of x equals f of xy and the g of xy equals 0 stuff. We don't care about that. Just let's just say that a general region is just a generally non-rectangular shape. It could be rectangle, but um, non-rectangular. And I'm not going to define this in the xy plane. So I'm not really going to define this any better than this. Um, but what they're doing here is they're saying you find a rectangle. And then what they're saying is um, you can define a function where um, inside a region, you have your function g is f of xy, and outside of that region, you have g of xy equals 0. And it's like, okay, um, so um, why do we care about that? Well, it's because they want to relate the integral over a rectangular region to an integral over the non-rectangular region that's inside of it. But I don't think we really care too much about that theory. So what I'm going to do is I'm just going to simply give you a definition um, of a rectangular region that does not use that, I don't think. So I'm going to copy it straight from the book. And when I say copy it, I mean literally copy paste it straight from the book because I don't want to draw all these pictures for you, and probably you don't want me to either. So here it is. This is what we're going to be talking about, general regions. So general regions. Um, type 1 and type 2. Now, I do want to say about these type 1 and type 2 general regions here that I've never made this distinction before. Your book does it, but for it's really just so they can refer to them as type 1 and type 2 and do less writing later on. So let's just read this definition and look at the pictures. So a region D, right? So like generally speaking, it can be any kind of shape in the XY plane. Um, whoa. A region D, stop that. Just let me highlight. Stop. Stop. Why isn't this working? Okay, now it's working. Weird. Okay, so a region D in the XY plane is type 1 if it lies between two vertical lines and the graphs of two continuous functions, g1 of x and g2 of x. So the key here for the type 1 is that your top surface is given as y equals something, and your bottom surface is given as y equals something. So you have straight lines on the edges, right? So type 1 is vertical lines on the edges, if there even are lines on the edges. You can have triangular type regions and stuff. There might not be lines on the edges. So vertical lines or nothing. on the left and right edges of the region D. And then the top and the bottom edges are curves y equals function of x. Um, the top, top and bottom edges are like y equals function of x. Okay, so they've drawn three cases here. So on this case, right, the top and the bottom edges are functions, and the left and the right edges are vertical lines. And on this one, the top and the bottom edges are functions again. You have a vertical line on the right. On the left, there is no vertical line, right? They just meet at a point here. And that's why I said vertical lines or nothing on the left and right edges of D. Third case here, top and bottom are functions, y equals function of x. And again, this time they meet at a point on both edges, so there's no vertical lines here or here. Right, so that's what they're going to call a type 1 region. Now, a type 2 region is just going to be kind of the same thing, but sideways. So this kind. So type 2 is going to be horizontal lines or nothing on top and bottom. But then the left and the right edges of D are x equals a function of y. Right? So just like this. Function of y, function of y. And the reason we care about type 1 and type 2 is because when you set up your integral, in one case you have to set up a y integral first, and in the other case you have to set up an x integral first. We're doing double integrals just the way we did them in the previous section, which, if you remember, means that you can do an x integral first, then y, or then the other way around, y and then x. So these are type 1 and type 2 regions, and the definitions of them are right here. So you can see what they are. So x is between constants, y is between functions in the type 1. Type 2, y is in between constants, and h is between functions. So simply what you see in the pictures and what I wrote, and also what I wrote is pretty much their definition as well. So those are those regions. Now there are some regions, I didn't make a picture, but I'll just draw a picture. Some regions are type 1 and 2. And then, like, as an example here, if you do like y equals square root x, and then you do like y equals x cubed, and you put d in between, that's a type 1 and type 2, because you can say top curve and bottom curve, but also you could think of it as curve on the left, curve on the right. So you could actually set it up either way. So like, for example, this region that I drew here, let's see here. I guess these would intersect at 1, 1, right? Yeah, that's 1, 1, and then this is 0, 0. Right, so if you wanted to list it as a type 1 region, so we're going to follow the definition here. So type 1 means x is between constants, y is between functions. So the way you would describe this is you would say, well, I can see that this is the, let me rewrite it so I have more room. The set of all x and y such that um, the x the x is between 0 and 1, so those are constants, which makes it a type 1 region. And your y is between functions, and the functions are on top, it is y equals square root x. And the bottom curve is actually this one, which is y equals x cubed. So that's how you would list it as a type 2 region. Now, as a type 1 region, sorry, did I say that type 2? That was type 1. As a type 2 region, you would say it's the set of all x and y such that, well, now we want bounds for y. Well, actually, the bounds for y in terms of constants are 0 and 1. So that part actually looks similar. And then for x, though, x is supposed to be in between functions. So the key here is noticing that both of these functions you could solve for x, write them the other way around. So if you have, like, for example, y equals x cubed for one of your curves, that would mean that if you just cube root both sides, you would have y to the 1/3 equals x, right? And for the other one, if you have y equals square root of x for your curve, then if you solve that one for x, x would be y squared, right? So the one that's on the left, the left would be this one, right? Because it's over, oops, left and then right. So the left-hand curve is the square root x one, which is this one. So you could also write it, though, as x equals y squared. And this one, which is on the bottom, you could also think of as being the right-hand curve, and that would be x equals y to the 1/3. Right? So just solve for x on both of these, and you can rewrite them with different names. And then over here, your left-hand curve was the y squared, and your right-hand curve was y to the 1/3. And that's how you would do it as a type 2 region. So if you have a curve that's on top and on bottom, but that's also on the left and on the right, then you can think of it as a type 1 or a type 2 region. And I don't think you really have to answer questions like that on the homework specifically, but you do need to understand it because when you switch the order of integration, we'll be doing that, and you'll see that. Okay, so yeah. Oh, okay. So formally, here's how they do it. So suppose you want to integrate over D, right? So this is going to be our definition here. You want to integrate over a general region D that happens to be inside of a rectangle R. And let's say we want to integrate f of x, y over a general region D that is inside of a rectangle R. So this is why you do need their definition. So I guess I'm going to do what I said I was not going to do. All right, so here's our picture. So what they do is you want to integrate this function f of x, y, and you want to integrate it over D. But you can't because right now we don't know how to integrate over a non-rectangular region. So if you want to integrate over a non-rectangular region, formally what you can do is you can define a new function So our old function was f of xy, right? That's the one that we want to integrate over. We want to integrate f of xy. So you define a new function, g of xy, and your new function is equal to f um, whenever the xy is in D. And it's equal to 0 whenever xy is not in D. And the idea then is if you integrate over the rectangle of g of xy, so you're integrating over the entire rectangle. Now we know how to integrate over a rectangle, right? Because that's what we learned how to do in the previous section. But the trick is we're integrating this function over a rectangle, but the function that we're integrating is 0 outside of D. So like inside this region, right? Like this is 0, 0, 0, 0, just 0 everywhere outside D. So that turns out to be the same thing as just integrating over D. And that's actually what the definition of integrating over D is. So since this function is 0 outside of D, integrating over R is the same thing as integrating over D. That's the idea. So integrating G over R is the same as integrating over D, because the function G, the function you're integrating, is just 0 outside of D. So like it doesn't matter if you integrate over this region, because since the function's 0, the integral's 0 there. So that means that integrating over R is the same thing as integrating over D. But if you're integrating over D of this function G, actually, since you're inside D, G is actually the same thing as integrating F. And so what you're able to say is that actually, and so the integral over D of f of x, which is what we wanted, is going to be defined to be the integral over R of that G. Okay, can be our definition of integration over a general region. And the point is, how do you integrate over a general region? Well, technically, you can make it a rectangular region, and you already know how to do that. That's the idea. Now, just like before, this is not, just like in the previous section, this is the definition of the integral. This is not actually how you do the integral. Okay, so keep that in mind. Okay, so the next thing is how to compute them. A double integral over a general region. All right, and what you use is the same theorem, at least it's called the same thing as the previous section. We use Fubini's theorem. Okay, and so here's what Fubini's theorem will be for a general region. So if your D here is going to be like the set of x, y, such that if you have x between A and B, and then you have y between, we'll say G1 and G2, like that. So this is type 1. Type 1. Then you want to do the double integral over D of fxy dA. And what you're actually going to do is you're going to do an integral from A to B of the integral from g1 to g2 of f of xy, and you do the y integral first, and then you do the x integral second. And so what's going on here is um, if y is in between functions, you put those functions as the limits of integration, and that's the integral that you have to do first. And you'll see that it makes sense that you have to do it first. So those are there, right? And then your constants, those go in the second integral that you do. All right. Now, if you're doing a type 2 integral, just everything is reversed. So type 2, it's going to be, so if D is the set of x, y, such that y is between constants, I guess we'll call them C and D, and x is between functions, they call them h here, h1 and h2. Then if you want to do the double integral over d of f of x, y, dA, again, if your functions are for x, you've got to do the x integral first. So you do integral from h1 to h2 of f of x, y, dx. And then after you do that, you do your integral from c to d, and that's what you do for d. And I could have put parentheses here as well, like that. Okay, and so that's what Fubini's theorem says. And this is not as hard as it looks. I mean, you see the functions here and, the definition of D, and then looks complicated. But so let's do an example. So let's start with the very easy one first. Let's just say draw a region, first of all. Do like that. Now, I drew that line kind of, looks like, oh, it's not slope 1. I don't know what it is. Let's just say it's y equals, say, 1, 2, 3, 4, 5. Yeah, let's say 5x over 4. Actually looks like it is. And then we'll integrate 1, 2, 3, 4, 5. Like that. Okay, so this is going to be our region D right here. Okay, and I want to evaluate the double integral over D of f of x, y, dA, where f of x, y could be any kind of function. I'm just going to pull one off an example here. Let's say e to the 2xy. Will I regret that? No, I won't. It'll be, oh, yes, I will. Yes, I will. I'm not going to do that. Let me change it. Let's go e to the 2x sine, no, y squared. Okay, this will be perfectly doable, I think. Wait. Sorry. It'd be 3, 2. What? You gotta, so these have to be kind of rigged in order to be doable. So, you know what? Fine, let's not do an exponential. We'll do exponential on the next one. Okay, here's what we're doing. Xy squared. Okay, so how would we do this? So first thing would be to recognize the type that it is, right? So since I see functions on the top and bottom, right? Mostly the top, but That's type 1, right? Because remember your pictures here. Um, type 2 had your curves on the left and right sides, and type 1 had your curves on the top and the bottom. And so this one, I'm thinking top and bottom. Also, it's listed as a y function. So if I wanted to treat it like a type 2 integral, I'd have to solve for x, and I don't want to solve for x. So I'm going to do it as a type 1. So since I see functions on the top and bottom, I'm going to do, I'm treating it like type 2. Did I say type 2? Type 1. Type 1. Okay, so what's your region D? You don't have to list this, but I am. So x is going to be between constants, 0 and 5. Okay, now y is between functions. On top, your function's clearly y equals 5x over 4, right? So that's here, 5x over 4. Now your bottom function isn't labeled, but you should be able to figure out that that's y equals 0. Okay, so you have to figure out those functions. Now, once you figure out those functions, we can set up our integral. So you do your integral for x on the outside, that'll be 0 to 5. For y, you go from 0 to 5x over 4, and then your function is xy squared. And we have to do the y integral first and then the x integral. Otherwise, it won't work out. Okay, so this is how we set it up. You have some problems in the homework where this is what you type in, or you fill in the blanks for the limits, basically, and the function. So you do need to be able to set these up yourself, just like we did, and then now we can solve it. Now evaluate it. Okay, so we have to remember how to evaluate these integrals from last time. So we do our y integral first. So we're treating x like it's a constant, and we need the antiderivative of xy squared. So we need antiderivative of xy squared. We're treating the x like it's a constant right now because we're integrating with respect to y. So x is just along for the ride, and the y is y cubed over 3. Okay? Now your limits of integration are 0 and 5x over 4. So you have actually functions to plug in for the y, right? So we have our limits there. Now we plug in our limits for x and subtract. Plug in y equals 5x over 4 and y equals 0 and subtract. So we get integral from 0 to 5. And then here we got x, 5x over 4 to the 3 over 3 minus x 0 to the 3 over 3. And then we're going to do an x integral. So you work this out. Of course, there's not that much to work out here. The only things you really can do is you've got this 5 to the third power. 5 times 5 times 5 is 125. In the denominator, you've got 4 to the third power. So 4 to the third power, 4 to the 3 is 64. So 64 from that, but then another 3 there. So times 3 is 192. So you end up with 125 over 192. And then for x's, you've got x to the 3, and then another x, which is x to the 4th. And of course, this just works out to 0. So this is it. Okay. So we did our first integral. Now that we simplified it, we're going to take our integral with respect to x. So now we do our second integral once the first one is complete. So antiderivative is going to be x to the 5 over 5. And we're going from 0 to 5. What can we do here? Well, first of all, one thing I can do is 125 over 5 is going to be 25. So it's 25 over 192, x to the 5th, from 0 to 5. So that's going to be 25 over 192, 5 to the 5, minus 25 over 192, 0 to the 5. Is that right? I think that's right. So of course the second one is 0 again. 5 to the 5, that's a very large number. 5 to the 5 is 3,000 something times 25, 78,000 something. Divide by 192 and you get, it's like a fraction. Oh, it won't even. Okay. Well, so my calculator won't fraction to decimal it, but 78125 over 192, or approximately 406.901. Now, some of the problems are going to need an exact answer in the homework, and some of them are going to need a decimal approximation. They'll tell you how many decimals you need if you need a decimal approximation. Okay, so that was our first double integral over a general region. So we integrated over a triangle here, and it worked out. Now let's try one that they give us, and we will see how it goes. This is another triangle though, but at least the function is going to be different. Example. So evaluate double integral x to the 2. Why are you doing this to me, computer? E to the xy dA, where d is and shown. So they draw a picture of it. Sometimes they list it and do math, and sometimes they draw a picture and just label the picture with what you need to know. So here they go y equals 1. And then they have a curve. By curve, I mean a straight line, 1/2 x. And then D is going to be this region here. And they label this point as 2, 1. Okay, so again, technically this is type 1 or type 2, whichever way you feel like doing it, because you can think of it as being a left function and a right function, or a top function and a bottom function. But we're going to treat it like type 1 again, because number 1, they told me to, I think. And number 2, it's already listed this way, right? Y equals a function, and that's a type 1 region kind of thing. So D, right, it's xy such that x is between something, y is between something. So for the x, if we're treating this like a type 1, you need to know what are the minimum and maximum x values. So, of course, that's 0, that's 2. So 0 and 2. Okay. Now for your y is between two functions. So the top function is actually y equals 1, right? So, I mean, here is y equals 1 is on top. Here, the straight line, the other line is on the bottom. So the top curve is actually just simply y equals 1. And the bottom curve is 1/2 x. Okay. Top curve, bottom curve. So we got to get them in the right order, or you'll get the negative of the answer that you should get. And yeah, so there's the region, and we can set up our integral, right? So the integral is, well, and I'll also just say it's type 1 because I don't think I wrote that anywhere. Um, so it's a integral. So the x is going to go between 0 and 2. The y is going to go between 1/2 x and 1. And then your function was whatever they said it was, x squared e to the xy. And, get used to this, right? This has x's in it, right? That must be the y integral is going to have x's in the answer. And then the other one is going to be the x, right? So there's our integral. So we set it up, type 1 integral, and let's get going. So 0 to 2, we're just carrying that along for the ride. And we need an antiderivative. So we need an antiderivative of x squared e to the xy, where, with respect to, I should say, y. Right? You have to make sure you pay attention to which variable you're integrating with respect to. So recall, think about this. If you were integrating like e to the 3y, right? Wouldn't that antiderivative be e to the 3y, and then you would divide by 3, right? That's what would happen with that constant. I know we've talked about that in the previous lecture as well. Well, the reason I'm mentioning that is because you're treating this x just like this 3, right? X is a constant. So when you go to do this antiderivative, it might seem weird, but you have this x squared, and then the antiderivative of e to the xy is going to be e to the xy over x, because you're treating x as if it's a constant. Okay, so that's a weird thing, but we did that. So we're here. Before you go and you substitute in these limits of integration, we should probably cancel one of these x's with one of these x's. So integral from 0 to 2, cancel an x, is just going to be x e to the xy from 1/2 x to 1. And that's, you're substituting that in for y. So 0 to 2. So you put a 1 in for the y's. There's only one y. So it's x e to the x times 1 minus x e to the x times, I lost, okay, 1/2 x. 1/2 x dx. Okay, so we end up with this integral, 0 to 2, x e to the x minus x e to the 1/2 x squared dx. Okay, so now this is just an integral. Now this is where you get sad, probably or maybe for the first time this lecture. But here's where you get sad, because you got to remember how to integrate. So you're going to split this up into two integrals. This one's going to take integration by parts, and this one's going to take integration by substitution. So you just got to remember your calculus 2 class in order to do these. So you have integral x e to the x dx minus integral 0 to 2 x e to the 1/2 x squared dx. So we split that up so I can do them separately, because this needs integration by parts. You could actually look up the answer, and this one's going to be a u substitution is what people usually call it. Let's do the u substitution first, because it's easier for people. So how do we do this u substitution? So you would do u equals 1/2 x squared. The du, you take the derivative of 1/2 x squared, it's going to be simply x, right? Dx. So when you make your u substitution here, you got x dx right there, and you've got your 1/2 x squared right there. So when you make your u substitution here, it's simply going to be e to the u du. Very simple. Now, I should also translate the limits of integration. Maybe I'll move this out a little bit lower, so a little bit more room. So you should translate the limits of integration. So if the top limit was previously x equals 2, and you plug that into your substitution here, the u would be 1/2 2 squared, which actually also is 2. Your bottom limit of integration was x equals 0. And if you plug that into your substitution, u equals 1/2 0 squared, you also get 0. So interestingly enough, you translate your limits and they go from 0 to 2 to 0 to 2. Okay. Since we already did this much, we may as well just finish this integral. So the antiderivative of e to the u is e to the u. We're evaluating that between 2 and 0. So you have minus e to the 2 minus e to the 0. And you will leave it there. We'll come back to this. Okay. For the other one, we are doing integration by parts. So let's remember how to do integration by parts, I hope. So for integration by parts, if you have a polynomial, which x is a polynomial technically, then you do u equals that polynomial. The dv is going to be the rest of everything. You go from u to du, which would be dx, by taking a derivative. You go from dv to v by doing an antiderivative. So the antiderivative of e to the x is just e to the x. And then the integration by parts formula is that the integral of u dv is uv minus the integral of v du. And so if you apply that formula here, what we get is that we need to write this out, the uv. So you have your uv first. uv is x e to the x, and then minus the integral of v du. V is here, du is here. So e to the x dx. To the x dx. So there you go. All of this should be, oops, jumped on me. All of this should be evaluated between 0 and 2 as well, because this is a definite integral. So we integrate e to the x dx, we're going to get e to the x. So what we have discovered here is that the antiderivative of x e to the x is x e to the x minus e to the x. And that is something that you could look up, but we didn't. We just did integration by parts. Okay, so now from here, you have to evaluate between 2 and 0. So you have 2e to the 2 minus e to the 2 when you plug in a 2, and then minus 0e to the 0 minus e to the 0 when you plug in 0. Now at this point, we need to just evaluate all of this. So let's just, work this out. And we'll get what we get. So 2e to the 2 is, well, 2e to the 2. Oh, wait, hold on. 2e to the 2 minus e to the 2. Okay. Try again. So 2e to the 2 minus e to the 2 is just e to the 2, right? Just 2 of them minus 1 of them. And then you've got minus, let's work this out. 0e to the 0 is 0, but then it's minus e to the 0, so that's minus 1. And then here we got minus, and then this is just e to the 2. So overall, you've got e to the 2 minus minus, so e to the 2 minus minus 1 minus e to the 2. And you work that all out, and it looks like simply 1. Something happened here. I have the wrong answer. Did I lose a number here? Yes, I did. I said e to the 0 is 0. So this is e to the 2 minus e to the 0. So that's actually e to the 2 minus 1. So when you come down here, it's minus e to the 2 and then minus minus 1. So there's another plus 1 there. Okay. So now if you actually add these up, e to the 2 minus e to the 2 cancel, but then 1 plus 1 is 2. Okay. Now I did that pretty quick, but you've got to remember all your rules for integration. So, I mean, that's integration by parts. Trig substitution could potentially show up. I don't think it does in this section, but it could. U substitution could show up a lot, and you just need to be okay at it. Okay. I linked some worksheets, not worksheets, handouts for you on like derivative and integration formulas. So you should be able to look up integration by parts and that kind of thing. Let's keep going here. Let's do one of these. That's an easy integral. Okay, but we'll do it because it's type 2. We haven't done type 2 yet. Sample. Evaluate double integral over d 3x squared plus y squared dA, where, and they're kind of nice. They it is nicer when they just list the region because you can go straight from this kind of description to your integral. So they say like that's supposed to be a y. Y is between -2 and 3, and then they say y squared minus 3 is less than x, less than or equal to y plus 3. Okay, so if you're going to do this integral, the first thing you should notice is what type it is. So you should be able to look at this and say, well, that's going to be the type 2, right? Because their functions are for x, your x integral has to be the one that you do first. So you go to set this up and you go integral, integral. The outside one is the one with the constants. The inside one is going to be the one with the variables, like that. Now then you got your function, which is just 3x squared plus y squared. And then what order does the integral go? Well, remember, if you got y's here, that's actually going to be your x integral has to come first. Also, x is right here, right? The y integral is this one. The x integral is this one, just based on what the functions are. So we do the dx integral first, and then we do the dy integral. So there's our setup. And again, you do have to do this on the homework, set up integrals. And let's go. So like I said, I think this one's going to be an easier integral because it's just polynomials. But let's go. Oops. We're going to do the integral from dy or dx right now. Okay, so we need to integrate this with respect to x. That's our first variable. So what's the antiderivative of 3x squared? X cubed. Now, what's the antiderivative of y squared? Well, we're treating that like a constant. So the antiderivative of a constant dx is x, constant x. So the antiderivative of y squared is y squared x when you integrate with respect to x. Yes. Okay. Now then we're going to plug these in for x, the limits of integration. So we're going to plug in for x. So we have y plus 3 cubed plus y squared y plus 3 minus y squared minus 3 cubed plus y squared minus 3. Ooh, do I have enough parentheses? No. So you get something like that. Now, by the way, can you work this out? Yes, of course you can, right? You're all smart. You can work that out. You can cube things and so on. But probably if you're like me, you don't want to. And that's where you want to use your computational tools here. So let's just work this out. So you just go, we got y plus 3 cubed. Then you go plus y squared y plus 3, like that. Then we got minus, scroll over. Careful to get this all in parentheses so you don't lose that minus. You have more parentheses, y squared minus 3 parentheses cubed, and then plus y squared parentheses y squared minus 3 parentheses parentheses, and I think that's all the parentheses we need. It does highlight like when you're, I mean, maybe that's because it's an iPad, I don't know, but it did highlight when I got the parentheses where they go. Okay, so I typed that all in and equals, right? And I do recommend that you, did I type in like an uppercase Y or something somewhere? It's not like uppercase Y squared. Ah, I did. Stupid me. Okay. I was like, why isn't it simplifying it? And then I saw the uppercase Y. So I'm going to scroll down until all the way until you find it in a form that you want. So, oops, the one that says expanded form, that's the one I'm going with, right? That expanded form is going to be the easiest one to integrate. So I'm going to go -2 to 3, and then just negative y to the 6th plus 8y to the 4th plus 2y to the 3 minus 12y squared plus 27y plus 54. And if you don't use tools like this that are available to you, your life is going to be hard. Okay. So we have this integral. You could do this on a computer as well, but we should, if you can do it by hand, do it by hand. Does that contradict what I just said? Maybe. Do I care? Maybe. All right. So antiderivative with respect to y. This is easy. Power rule. Power rule. Power. I just momentarily confused myself. Power rule. Then you use the power rule. And finally, technically, still the power rule. Okay. Then you got to put in a 3 here. And I am about to use a computer. But, make sure you do understand fully what you're doing before you go and punch this into a computer or a calculator. So I'm just gotta just keep going here. Keep on keeping it on. I am absolutely not even going to work this out. Okay. So what is that? I'll tell you what it is. Here's what I'm going to do. You go back to Wolfram Alpha, like so, and I go to this expanded form. I was going to copy paste it, but I clicked on it and it just brought me here. So that's the thing that I'm supposed to integrate, right? So then you just go like this. You go up here and you go integrate that from y equals -2 to y equals 3. You double check that it did type it incorrectly. Um, so you do that, and then you get 2375 over 7, which is approximately 339.29, right? And if you don't do that, then your life is going to be very hard if you try to work all of that out every single time on these problems. So I really recommend it. Also, if you do get stuck on some integral, again, Wolfram Alpha is your friend, right? Like you set up this integral and you're here, and if you understand integration by parts, like for example, um, but like if you forget how to do that derivative or antiderivative, for example, you can just go like here. This is the previous problem. You can just go like, oh, I forgot what the antiderivative of x e to the x is, or how to do it. And if you just need the answer, you can get it from here, right? Expanded form, e to the x x minus e to the x, which of course we would have gotten, right? X e to the x minus e to the x. You could integrate that from 0 to 2 as well. If you're trying to figure out how to do it, Wolfram Alpha is not your best bet. What is your best bet would be symbolab.com. This site is good for checking integrals because if you wanted to know how to do this, you can find the integral symbol, the list of things it does, and then you can. It's not the easiest on an iPad here, but I can go 0, 0. Oh, I forgot. Um, Symbolab is sort of broken on an iPad. So when you hit a key, nothing happens. And then when you hit the next key, you get the result of the previous key that you hit. What it means is that I'm going to type this everything in wrong over and over here. X, see, I just hit X and it said 2 because the last key was a 2. X, okay, E, delete, E, delete, E, okay, got it. Okay, got to get an X up there. Got it, finally. Did that work? Was that correct? Okay. Okay. All right. So, on a device where you can just type in properly, that's not so hard to type in. Um, Now, the reason you might want to use Symbolab to do an integral like that is because you'll see it says it tells you that you do an integration by parts, and if you go show steps, oh, um, it used to show you steps on more stuff, but all right. Well, at least it still says apply integration by parts formula, and then they gave you that result, um, and then and so on. So it does show you more steps for free. You could get even more steps if you pay them money, but I would not recommend that. But Symbolab is a good tool for evaluating integrals and derivatives. Okay, there we go. All right. So, I mean, we did a couple of those. We did a type 1 and a type 2 integral. Let's move on. Um, let's just talk about how you would do an integral here. I'm not going to do this next integral. I'm going to talk about how you would write it out. Um, so let's see. Set up the integral, actually integrals, for double integral over d of 2x plus 5y dA, where, and we've got to draw a picture here. So, okay. So what's happening is you got 0 minus 4 down here. Straight line. Straight line, straight line. This is negative 2 comma 0 right here. Then this goes up like this. This goes up like this. This is at supposedly 0, 4. And then there's a curve like this that keeps going like this. Okay. And this curve is y equal, nope, no, it isn't. This curve is x equals y minus 1/16 y to the 3. And this curve is y equals x plus 2 squared. Okay. And so this is a very complicated looking shape. Oops, not what I wanted. This will be fine. Right, so this is the actual region that we're trying to integrate over. Now we're not going to do the integral, but we're going to set it up. Okay, so that's pretty complicated looking, and we have to figure out what to do here. And so the main thing is that you can't just set it up with a single integral, because which integral is on top or bottom, or which integral is left and right, changes over different pieces of the graph. So in order to do this, you have to think of it this way. So you have to, let me get a better color. To set it up, you'll have to do this. Have to split D up into two pieces. So what are the pieces? So let me just copy this. Do a better job copying it. Duplicate it, move it down here. So the two pieces that you want are going to be like this. So you're going to do one here, top half of the graph, like maybe I call that D1. And then the bottom part of the graph, like that, maybe you call that one D2. Because when you're going to write the regions now, you can say that D1 would be the set of x, y such that, and so what you could do is you could say in that region, the y value starts at y equals 0, right? So the y value could be between 0 and 4, right? The y value goes between 0 and 4 in that section. And then the x value, which I didn't leave myself enough room to do, so let's move this over. The x is between this curve on the left and this curve on the right, which the curve on the right is already written as an x equals, so that's good because you can do x less than y minus 1/16 y cubed. But the other side, it needs to be x equals, and we don't even have, like, I don't know yet. I'm just gonna leave that blank because it's this curve, but this is not solved for x, so we can't use it yet. Okay, so we'll leave that blank for the moment. Now for the D2 region, it's the set of x, y such that, and I think we'll do it the same way. Y could be between minimum and maximum y values are -4 and 0, right? -4 up to 0 there. And then your curves on the left and the right, though, are going to be a little bit easier. The right-hand curve is actually the same as the right-hand curve here. This is one curve. So the right-hand curve here is still going to be y minus 1/16 y cubed. But the curve on the left-hand side is just here, which is just actually x equals -2. Like that. Okay. So for that question mark, for the question mark part, you have y equals x plus 2 squared, but we need it solved for x. Right? Because it goes there, and that's x greater than something. So it needs to be a function of y. So you have to solve for x there. And which you can, right? It's not super complicated. You square root both sides. Technically, there's a plus or minus there. We'll have to consider that. And then you move the 2 over. So square root y minus 2 equals x. Yeah. Okay, and then just double check that you actually get the right thing, right? Because if you plug in a 4 for y, you're supposed to get a 0. So do you get a 0 if you plug in a 4 for y? Yes, you do. And when you plug in a 0 for y, right, this is -2, 0. So if you plug a 0 in here for y, you get -2, x equals -2, which you do. So that's correct, because technically this could have been a plus or a minus, and it's actually the plus because just checking that if I plug in like this point here and this point here, like the y equals 4 and the y equals 0 in here for y, I see that the plus sign is the one that actually gives me the values I see on the graph. So this is what we want. This is what we want. So once you know that, then that's that. So now we can finally set up our integral. So our integral is actually going to be the double integral over d of the function, which we did have the function, right? It was 2x plus 5y dA. And we're doing these as a type 2 integral, I guess. So you do one integral over the d1, 2x plus 5y dA, and you're going to have to do a separate integral over the d2 of the 2x plus 5y dA. So first integral, the outside integral for d1 is going to be y between 0 and 4. The other integral is going to be between the question mark on the bottom, which was y minus 2, The top curve is this y minus 1/16 y cubed, and then you've got your 2x plus 5y, and it's a dx and then a dy. Um, yes. Then, plus the other integral, which I should have left a little more room, which is g2, and we've got there -4 to 0 for the y integral, and then -2 to y minus 1/16 y cubed 2x plus 5 dx dy. And so you have to do all that just to set up this integral. And you don't have to do this very much, but it is something that theoretically you could have to set up. So the region's complicated, then it takes a little bit of effort. You might have to divide it into sections and do them separately. Okay. Next thing, we want to talk about changing the order of integration. So the idea is pretty simple. So you know that already some regions could be type 1 or type 2. Right, we already know that. And the other thing is that it's possible that you have an integral that's one type, but if you were to change it in the other type, the integral would be easier. So it's possible that you have an integral like a type 1 integral, for example, but if you would rewrite it as a type 2, the integral would be easier. Right, or the other way around. Right, there's nothing special about type 1, type 2. So that's the idea. So presumably it would be easier for some reason. So like here's an example that they give, and we'll see how to reverse the order. I think I'm not going to do the integral because we got more stuff to do. Okay. So 0 to square root 2, 0 to 2 minus x squared, x e to the x squared, dy dx. And what they want me to do is I want to reverse the order of integration. Okay. Yeah. And I'm not going to do the integral afterwards, but you could. So I just want to reverse the order of integration. So the way I would go about this is, first thing I would do is I would draw the region out so I could look at it. Okay. If you don't do that, your life is going to be tricky here. Okay. So I'm going to draw the region. And then after I draw the region, I will figure out how to reverse it. And there's not really a lot to say there. It's like once you draw the region, then you know how to set it up in the other type because you know how to set up both types, right? So figure out how to switch the order. So draw the region D, and then we'll figure it out from there. So let's do this. So you should be able to read off the region just based on the way the integral is, right? You see that the inside integral is y. So that's the first integral you do. And then your second integral is x. x is the one that's between constants. So you have x between constants 0 and square root 2. And you have y between functions, and your minimum function is 0, or minimum lower function is 0, and your upper function is 2 minus x squared. Okay, so that's the region. So if I'm going to go ahead and draw this on the graph, it's trying to get a straight line. Okay. I don't think we need negatives here. So first of all, you could graph this, right? So the bottom curve here, so the bottom curve is y equals 0. That's from this. The top curve is y equals 2 minus x squared. That's from this. Okay, so you have to graph these. You have to graph these two curves. So y equals 0 is easy, right? So you just go y equals 0, easy. Y equals 2 minus x squared, that's an upside down parabola that goes through 2, right? So you go, okay, well, I did not want to erase that. Stop erasing. I'm not on the eraser. Come on, man. Good enough. I can even move that over, actually. Or to put in the right place. Okay. So that is y equals 2 minus x squared, right? Use a computer if you don't know what these look like. So there you go. There's your curves. Now, then you've got your x curves. Your x curves left is x equals 0, and right is x equals square root 2. That's from these, right? So x equals 0 is here, and x equals square root 2, you'd have to figure it out. One thing you might want to think about is like, if you put this square root of 2 in here, 2 minus square root of 2 squared is 0. So actually, this intersection point is square root 2. And so your region is this region. Okay. So there you go. So do that first. We figured out the region. Okay. Now what we want to do is we want to rewrite that region. So I'm going to redraw this picture so it hopefully looks slightly better. So D is here. And I know that this is up at 2, and I know that this is over at square root 2. And of course this is, so there's our curve. And then this curve was listed as y equals 2 minus x squared. And so we want to switch the order of integration. So if we want to switch the order, then our region D is going to be a set of x comma y such that we did have x was between constants. Now we want y to be between constants. So if y is in between constants, what are the constants? Right? So you'd have to figure that out from the graph. The bottom for a constant is 0, and the top is 2. So you get those. Okay? And then for the other variable, in this case, x, right? What's the minimum and maximum curves? Well, the x is going to be greater than 0, right? Because x equals 0 is right here. So if I do like x equals 0, 0 right there. And then over here, this curve, this is x equals something, right? But I don't know what. In order to get the what, I'm going to have to take that curve and I'm going to have to solve it for x. So I have to solve y equals 2 minus x squared for x to get the top limit. And again, we've done this a couple times, right? So like move the x squared over, you get x squared minus, no, plus y equals 2. Subtract y from both sides, you get x squared equals 2 minus y. Then you square root. Technically it's plus or minus, but we do want actually positive x values, right? We're on like negative x values are over here, positive x values are over here. So technically there's a plus or minus, but we want specifically the plus. So you do that. So it's basically you draw the region and then you start setting it up from scratch, right? So once you have D drawn, it's just like a new set up the integral problem. So you just do it the way you would any set up the integral problems. Just make sure you actually do write it in the opposite order this time. Otherwise, you'll get the same answer that you started with. Uh, so that's switching the order of integration. Draw the region, then switch it. Okay, let's see here. So yeah, let's do areas. I gave this at the end of the previous lecture, but I'm going to do it again. So let's say let D be a region in the xy plane. You can draw it, whatever it is. Okay, so you've got a region in the xy plane, and the area of D is the double integral over D of just dA, or 1 dA. So if you just leave out the function, you're actually calculating um, the area, right? So it's just using like f of xy equals 1 in the double integral of d of f of xy dA. Right? That's all we're doing. And that's just by definition, not by definition, but by the way we define the double integral, that's the area, right? We add up all the areas and we get the area. Add up all the little dAs. So let's do an example of that. We did not last time. Um, so compute the area with a double integral. Now, there's some of these that you could do in Calculus 1, right? You did know how to calculate areas in Calculus 1 using a single integral. So this is going to be y equals 2x. And then do a parabola. If I can draw a parabola. Well, oh, I can. Oh, dang, that's nice. So that's y equals 2x, and this is y equals x squared. And we want the area between them. Okay, so how would you do that? And this, by the way, where they intersect is the point 2 comma 4. Okay, so how would you do that? Well, we know it's a double integral over d of just dA, which is dx dy, or dy dx, depending on which way you do it. So how would you describe this region, right? You got to think about how to do that. It's going to be, I guess it doesn't matter. I guess we'll do y between 2x on the left and x squared on the right, 2. And then that would mean that x has to be between constants, and this constant is 0, and this constant is 2, right? So 0, 2. So you got to get better at writing out these regions. Once we write out the regions, I can say that the area is now going to be an integral 0 to 2 for my x integral, 2x to x squared for my y integral, and then you do the y one first and the x one second. Right? Now, if we actually do this, so let's just evaluate and see what happens. So if you integrate 1 dy, you just get y. And you evaluate that between 2x and x squared. And so you get the integral from 0 to 2 of x squared minus 2x dx. Now, the reason I want to mention this is just kind of like a note here. Note. In Calc 1, you would do like the area is equal to an integral from a to b of the top curve minus the bottom curve, and then like dx, right? And if you work that out here, your a and your b would be 0 and 2. Your top curve is that 2x, which as soon as I write that down, I realize I switched this order here. X is between 0 and 2. Like in my head, I did this like I was doing left curve, right curve for bottom, top. But this is clearly the top and this is clearly the bottom. So I put those in the wrong order. Oops. Which means you got to fix them here. 2x x squared. Which means you got to fix them here. 2x x squared. Which means you have to fix them here. 2x x squared. Okay. So in Calc 1, you would have done this with top curve minus bottom curve, and the top curve is y equals 2x, and the bottom curve is y equals x squared. So you would have set up this integral, you would set this integral up directly, whereas here it takes us a couple of steps to get there. But obviously we're going to get the same answer now. So it's the same as what we end up doing with the double integral. All right, so the results are the same. Nothing fancy. So if you actually do this antiderivative, now we're integrating with respect to x, we get x squared minus x cubed over 3, power rule, plug in the 0 and 2, 2 to the 2 minus 2 to the 3 over 3, minus 0 squared minus 0 to the 3 over 3. This is 4, it's about to write an 8. 4 minus 8 thirds, just 4 minus 8 thirds. So you grab a calculator, 4 minus 8 thirds. Wish this calculator worked. And you get 1 and a third, or 4 thirds. Okay, so that would be how to calculate the area with a double integral. But any area that you can describe, you can evaluate the area with that formula. Just area is double integral over d of dA. So you just put a dA there, and then it's an area. Okay. Another thing we can do, which we haven't done, is average value of a function, which I should have given you this formula in the previous section, I think. But it's here. All right, average value of a function. So in Calc 1, the average value is this. Average value of f of x for x between a and b is 1 over b minus a integral a to b f of x dx. Okay. In Calc 3, average value of f of x comma y for, now you have to be careful here. What are we integrating over? We're integrating over a domain, right? A region D for x in D is 1 over the area of D integral over D of f of x y dA. So that's an analogous formula, right? Like b minus a, like b and a are the bounds here, and d, like the bounds for d, are basically the bounds here. So it's an analogous formula, and basically what you're doing is you're summing up the function over the region and then dividing by the area of the region, and then that gives you the average value in some sense. So this is like, we would call it like f average. But then what is the area of D, right? Remember that the area of D is an integral. So actually this is the integral over D of f of x y dA over the integral over D of just dA. So you actually have to do two integrals in order to solve this. Unless you're in the previous section, in which case the area of D is a rectangle, and there's easier ways to calculate the area of a rectangle than with an integral. Okay. Do I have to do one of these? I think I don't want to, because I want to get to improper integrals. So we'll do improper integrals, and then maybe we'll do one more example here. So an improper integral is going to be one where D is unbounded. It is called improper. What's an improper domain look like? For example, could look like this. Right? Like something like that, because the region goes out forever that way to the right. Or sometimes sometimes they just do something like this, where they just say like the entire uh, this would be like the entire first quadrant, for example. So, like regions like that are called improper. In order to calculate them, you have to use limits basically. So, I guess they have a Fubini's theorem here, but I don't want it. I'm just going to give you the theorem. So if unbounded rectangle, okay, fine, we'll do that, I guess. Okay, there's another type as well. So hold on, let me just go back. Um, Also, if you have some discontinuities, so if a function becomes unbounded, that's also improper. So unbounded on D, um, that's improper as well. So, like for example, um, here's the example they give: double integral over D of 1 over 1 minus x squared um, minus 2xy dA, where they say x squared plus 3y squared is less than or equal to 1. So, like, so I would assume that they're saying that somewhere in here, this is you're going to get a divide by 0, but I'm not going to look for where that is. I guess 1 comma 0 works. I mean, yeah. So those are also improper, and let me read this theorem here. Okay, well, yeah, forget it. We're just gonna go on and we're gonna do a an example of the first kind here. Um, or actually, no, we'll do an example of the second kind. You know what we're doing. We're doing an example. So we're going to evaluate this. We'll discuss it in detail. So sorry if I'm being confusing right now. I just don't know what examples I wanted to do. Okay, so we got a function. Consider the function f of x y equals e to the y over the region D, which is the set of all x comma y, such that 0 is less than x less than 1 comma x less than y less than square root x. And so looking at this region, right, you can see that this is discontinuous at 0, right? So at um, 0, 0, which is in D, right? Because 0, it's not what I wanted, it is 1 point. 0, x equals 0 is allowed. And then if this is a 0, then y could also be 0. So at 0, 0, which is in D, um, e to the y over y, right, which is f of x, y, is not defined. Okay. But as long as the number of discontinuities is finite, probably countable is also allowed, but we don't know that word. As long as the number of discontinuities is finite, uh, then the integral is actually just fine. Okay. Now the reason for that is because if you think about your kind of domain, right? D. And if you have just like one point where it's not continuous there, continuous at one single point, what you could think about doing, which we don't formally do this at all, so don't feel like we're about to do this. But what you could do is you could say like, well, what if we just change D to just leave that point out, right? What if we just use this D instead, where we just left out that one single point? Right? So you just leave out that point, put a little circle around it, and then we do like the integral for d2, um, and let like that little circle area of the little circle go to 0. Right? That way we leave out the point. That was a problem. Out. Okay. And the point of what I'm trying to say here is that there are ways to handle it, even though we don't. Okay. Um, so what would we actually have to do? Well, I mean, I don't think we do anything. I think we just do the integral. Um, so, uh, so like, how would you do this integral? Just do it. Um, so let's try the integral, even though we know 0, 0 is a problem. So if you were going to do this integral, the integral would be double integral. Our function is e to the y over y. We have our outside integral is 0 to 1. Our inside integral is x to square root x. As they said so. Do we have to change the order here? I think maybe we do. I don't know. I don't know. I'm just writing it this way. We'll probably have to change the order here. Hold on. So we have that. That's a dy integral and then a dx integral, the way we wrote it. Now, I think that's right based on what we saw here, right? X to square root x for y. Yeah. Okay. Now, however, you get to this point and you realize that you don't actually know how to integrate this. I think, right? We don't know the antiderivative of e to the y over y. Seems to be a problem. So we'll switch the order. which is why we learned how to switch the order. So what's the region D? So the region D, if we draw it, I think we can. Um, y was between 0 and 1. No, that was x actually. Um, x is between 0 and 1. Okay. Y is between x and square root x. So y equals x is a straight line like that. This is y equals x. And then square root x looks like this. And then the region D is the region in between there. And the problem point, by the way, was right here. But again, we're just going to ignore it and hope it doesn't cause an issue, is all we're going to do. So there you go. How are we going to integrate it? Well, we would need to solve these the other way around, right? So y equals square root x and y equals x. And I want to solve for the other variable, so solve for x. And then what we'll get is y squared equals x, and well, just y equals x. There's nothing to do for that one, right? So you call this x equals y, and you call this one x equals y squared. Okay. Also, that point is 1, 1. So once you do that, we can say that D is the D that they wrote, but we could call it instead of x between 0 and 1, we could call it y between 0 and 1. And then x, we need the left-hand curve is y squared, and the right-hand curve is x equals y. And so that's the other way to write the region. So we switch the variables. So the integral we could do is this. So the integral, this integral, it's still e to the y over y, right? We didn't change that. But now we're going to do the y integral second and the x integral first, which is y squared for the bottom curve, y for the top curve. And that's an x integral and then a y integral. So we switched the order of integration from dy dx to dx dy. And why did that help us? Well, let's find out, right? We're going to actually do this integral then. So we integrate from 0 to 1. We need to integrate this with respect to x. Now, the reason that works out nicely when we do this integral is because there is no x. So e to the y over y is just constant. So if you do the antiderivative with respect to x, the result is just going to be e to the y over y. That's a constant times x. And then you go from y squared to y. So we put in the y, we put in the y squared. You're going to get e to the y over y minus e to the y over y squared, like this. 0 to 1. We do a little bit of canceling here. Cancel, 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 cancel. We end up just with e to the y, and then here we end up with y e to the y dy, right? And so we were able to do that integral, and we're able to do this integral too. So we can do this one. Right? And we already did the integral of x e to the x. Remember, you can do like u equals y. We can do dv equals e to the y. So du is dy, v is e to the y. And then when you do your uv minus integral v du, you get y e to the y minus the integral of the v du is e to the y dy, or y e to the y minus e to the y, right? So that's the same integral we did with integration by parts before. So we do this antiderivative here. The antiderivative of e to the y is e to the y minus the antiderivative of y e to the y is y e to the y minus e to the y. And we integrate from 0 to 1. So double checking this here, e to the y, e to the y minus e to the y is actually 2e to the y, then minus y e to the y, 0 to 1. So put in the 1, minus, then you put in the 0. This is 2e minus e minus 2. So 2e minus 2, and that is e minus 2. Yikes. But what was the point? The point was the fact that the function was discontinuous at 0, 0 did not stop us from doing the integral. Switching the order had nothing to do with the fact that it was discontinuous. So point is that although e to the y over y is not continuous at 0, 0, which is in D, the integral worked out fine because it's just a single point. Okay, switching the order had nothing to do with that issue. Okay, so let's look at unbounded regions and then that'll be it. Regions. Now that's just, we already mentioned what that might look like, but here's an example. So if R is an unbounded rectangle, such as R equals XY such that, like if you do like this, like X goes out to infinity, and then also Y goes out to infinity. So what would that look like? What that would look like is you put like an A there and you put like a C there, and then your region just goes out forever in those directions. So that's just an unbounded rectangle. Like it would be a rectangle, but there's no top and there's no side. Okay, so that's what we're talking about here. And the way you would evaluate this is what you would do is basically you do it with a limit. Like normally our integral is from A and like there's normally a B there, right? And normally we put a D there where it's C less than Y less than D. And so what you do is you say, well, the integral over D of f of x, y, dA is going to be, what you do is you just do the integral from A to B and from C to D. I guess that would be dx then dy. But remember, there was no D and B. Those were made up, right? It was actually infinity and infinity. So what you do is you say, well, the B is supposed to go to infinity and the D is supposed to go to infinity. So you put a limit here, and they actually do a double, like a two-dimensional limit there. You could do those as separate limits, but they didn't. And there's another way to do it, which is you can just switch the order of integration and do the y integral and then the x integral. But you still have to do that limit as, I said axy. It was the b and the d. And here it's still also the b and the d. Okay, so you just evaluate with a limit, which is like what you did that's like what you did in Calculus 1. It's just now you got fancier limit. Let's do one example. Evaluate the double integral over r. They use r for rectangle. Xy e to the negative x squared minus y squared dA over the entire first quadrant of the plane. All right, so I mean, first thing is making sure you understand what they mean for the region. So, I mean, I think we've drawn it, but right, D, like that. So D is the set of all xy such that x goes out to infinity and y also goes out to infinity, but they're positive, right? Because it's the first quadrant. So how would you set up this integral? Well, it'd be the limit as bd goes to infinity infinity of integral xy e to the negative x squared minus y squared. What do we want to do? The x integral or the y integral first. Now, if you look at this carefully, though, like there's no difference between the x variable and the y variable here, right? Negative x squared, negative y squared, same difference. Xy. So there's no reason to prefer one order of integration or the other one. So you can do either. Just make sure you use the correct limit. So if I do the x integral first, then I'm going from a to b, actually 0 to b, right? Because that's going to be my b and that's going to be my d. And then my y integral is going to be also 0 to b. So this is the integral we have, and then we can try to solve it. So the way you would solve this is when we do our x integral, then we're going to do a u substitution, right? You're going to say like, let u equal negative x squared minus y squared. And then your du, right? We're taking the derivative with respect to x. The derivative of negative x squared minus y squared with respect to x is negative 2x dx. So x dx is negative du over 2. Okay. So got a lot of writing. We substitute that in. I've got the y, which I'm not bothering to substitute. The x dx is du. I still have a dy out there. And then my e is going to be e to the u. So this is the integral I've got now. I didn't change those limits because I'm going to go back to the original variables. So I'm not going to bother. All right. So we need to integrate this now. And these are x limits, not u limits. Okay. So what's the antiderivative of y e to the u with respect to u? We're treating the y like a constant, right? So the antiderivative of e to the u is just e to the u. So like that, you get that. Um, but then these limits are for x, not for u. So I'm just going to leave that like that. So you actually have to substitute back if you want to use the 0 and the b, because the 0 and the b were for x. So you substitute back. Again, I'm just going to keep writing that. We put in the b, we put in the 0 for x. So you have y e to the negative b squared minus y squared minus y e to the negative 0 squared minus y squared dy. 0 to d, we got y e to the negative b squared minus y squared minus y e to the negative y squared dy, limit of something. Okay, how are we going to do these? Well, looks like each one needs a u substitution. I guess I could use like u and v or u and w or something. So like here you would do like u equals negative b squared minus y squared du, taking the derivative with respect to y this time. I just realized I just messed something up. I have to go way back. What about the negative over 2? So there's like a negative 1/2 out here in front now. I'll put it way out here. Now it's not in the way. Okay, sorry about that. So u is negative b squared minus y squared for this integral. So the derivative is negative 2y squared. No, it isn't, negative 2y dy. So dy is du over 2 negative again. You also have to do the same sort of thing over here where you're going to have like another substitution. I'll call it w. Like w is negative y squared. So dw is negative 2y dy. So over here, dy is negative dw over 2. Okay, so we got some nonsense going on that just closed. I hope it didn't leak very much. It just like force closed on me. Okay, we're where we were. We just lost a 2. Okay, so I've got this negative 1/2 that was from the first integral that I'm just carrying along. I'm not going to write out that limit still. Then I've got this integral here from 0 to d of y e to the negative b squared minus y squared dy, and separate integral of 0 to d of y e to the negative y squared dy, right? And all of that still has that limit on the outside. So using my substitutions here, I have the integral from 0 to d of, well, we got to make the same substitution, right? So like this is du over 2 is y dy. My brain is just at it today, I think. We fix these. Okay. Okay. So when you go to do these integrals here, you have the y dy is negative du over 2. And then your e to the u is right there. Now for your other integral, you also have 0 to d. Those are for y, not for u. Same thing going on here. The y dy is negative dw over 2. So I have negative dw over 2 e to the w. And so I had to do 2 substitutions there. They're almost the same substitutions. One thing I can do is, since these both have an over 2, since this one has a negative over 2 and this one has a negative over 2, we may as well take that out front of the whole thing and integral from 0 to d of just e to the u du minus integral from 0 to d of e to the w dw. Of course, these are easy integrals. Just e to the u, and that's from x goes from 0 to d, minus e to the w, and of course that's x goes from 0 to d, not the w. So before you substitute those 0 and d in, you've got to substitute back to the original variables. So for the u was negative b squared minus y squared. That. And now that's, I guess that's not x, that's y, right? Dang. Y. From y goes from 0 to d, and e to the w is negative y squared. And that's from 0 to d as well. So finally, we're within spitting distance of the answer. Don't spit, spitting's gross. Put in the d, put in the 0 for y. So we have e to the negative b squared minus d squared minus e to the negative b squared minus 0 squared for that one. Then here we have minus e to the negative d squared minus e to the negative 0 squared. Okay. Let us, again, I'm not doing the limit yet, so let's work this out a little bit. E to the negative b squared minus d squared minus e to the negative b squared. This is going to be minus, this is going to be minus this, which is going to be just minus this. And then you've got minus minus, which is a plus. E to the 0, what's e to the 0? E to the 0 is just 1, I think, right? Okay. So we're getting there. Now, let me go put my limit back in. So my limit was that b and d were both going to 0, or both going to infinity, sorry. So if you put that in, you get 1/4 e to the negative infinity squared minus infinity squared minus e to the negative infinity squared minus e to the negative infinity squared plus 1. And remember that, like, e to the negative infinity is 1 over e to the infinity, which is 0, right? So this is just 1/4, 0 minus 0 minus 0 plus 1, or 1/4. So there you go. We did an integral. That integral was kind of a lot of bullshit, to be honest, but we did it. Maybe it's just because it's late, but that was more trouble than I would have preferred. So we had to do u substitution just 3 times in there, and then some limits, and it worked out fine. And I was kind of not the most rigorous as far as how I was doing those limits. I did them correctly, but I didn't necessarily explain why everything was justified while I was doing it. But anyway, there you go. That's how you can do a limit over an infinite region. And I think that I'm not going to do one of those average values, just because, I mean, an average value is just do an integral, divide. And so if you come across one, you just have to know you do that. And remember the interpretation that the denominator there is actually just the area of the domain, because If the domain's a rectangle, you don't need to do an integral for it, right? You just need to figure out the area of the rectangle. So I think that's everything I wanted to say here. We're over 2 hours, so that is plenty long enough. Good luck on this. It's really just integrals. So the reason this lecture was long was because I did lots of integrals, um, not because there was a lot of theory in here, right? Just practice doing integrals with integration by parts and substitution and all of that. Anyway, I will talk to you guys later. That's it for now.